My background, if you go back a while, is in text mining, natural language processing, information retrieval, that kind of thing. And although these days I work mostly on kind of recommendation and personalization related problems, I think my background kind of influences how I think about some of those problems. So a lot of the techniques are kind of adaptable from text domains to other domains of interest. So I think that's kind of what motivated this talk. So the talk's about how to learn deep representations for unordered sets of items. And let's step back a bit and talk about what I mean by that and where it's useful. So a lot of real world data, particularly if you work in kind of e-commerce or social or, you know, the app industry in general, tends to consist of collections of objects. So, for example, a user's visit to a website can be thought of as a list of individual events, which is ordered, right? The products in a shopping cart can be considered like a bag of items. The words in a product's title is a list of words, right? The songs in a user's listening history, if you're doing music streaming, that's an ordered list of items. And the movies in a user's sign-up flow is a set of items. And quite often we want to be able to do recommendations or predictive analytics of some sort based on these collections of items. So some of those are very clearly ordered, right? So the events which occur during a user's visit, they have a very natural order. The songs that are played in a user's listening history, they have a very natural order. And of course, their tastes might evolve over time if they've been a customer for a service for a long period of time. Now, in other cases, that distinction isn't necessarily so clear, right? The products in a shopping cart, they could be ordered. If you're an e-commerce site and you know what order they traversed the site and what order they clicked add to cart, okay, there might be some information there. If you're if you're a bricks and mortar retailer, rather, so you're looking at, you know, data gathered from loyalty cards, nectar cards, or something like that. Maybe all you have is the order that those items went through the till at checkout time, and not necessarily the order that they added them to their physical cart as they go around the shop. And even if you did know the order they added them to their physical cart, that probably isn't that useful from a recommendations point of view, or for targeted marketing or whatever. Product titles, you'd think, well, a title, you know, that's almost like a sentence, right? That's got some order to it. But at my previous job, I worked at Etsy, and one thing I noticed working with product titles that were supplied by users a lot is they're quite often more like just collections of keywords. They're bags of terms and keywords that people have stuffed in there to try and improve their SEO. And the order may not necessarily be that important. Maybe the individual local ordering of pairs of words might be significant, but the overall order of things in that title may not be. And say you're signing up for a service like Netflix, for example, and you're given some options at the start to click on to show what your tastes are. You know, I like this movie, I don't like this movie. If there is any ordering information there, it's probably more of a function of what order the site presented you those options, rather than, you know, anything that really bears any meaning. So it's useful to have an idea of how to compose these collections of objects into like high-level representations that we can use in deep learning. Hang on. So yeah, if you do have ordered collections, you know, lists or sequences of some sort, there are pretty well understood, effective ways of putting those together to get higher level representations. So recurrent neural networks, or their more sophisticated offspring, like long short-term memory networks or gated recurrent units. So the input for those will be like a sequence of item embeddings usually, and the output might be an embedding for the whole sequence. They're very effective at these kind of sequence learning tasks, but they might not be always the cheapest things to train or the easiest things to train. And if the data's unordered, well, you could feed it through like an RNN or something, but you might risk like learning the model picking up things which are really artifacts of this artificial ordering that you've given the items or something. Or like maybe if they're kind of weakly ordered, you could put them through an RNN, but the overhead of actually using that might not be worth it for the extra benefit you would achieve from using that ordering, where there might be a cheaper way that discards the order information and does just as well on the task at hand. And that's really what this talks about. How can we learn a single embedding from a bag or set of item embeddings in a way that's more efficient than using the order that they're presented in? Or how can we learn an embedding from a bag or set when they have no order to begin with? So really any ordering that you did use was spurious or misleading. So there's one simple approach you can use, which is to initially learn embeddings for those items in an unsupervised manner, and then simply average them across all of the items that appear in a particular set or bag in order to get a composite representation for that set or bag. So one way, for example, is there's this paper, I think it was from Microsoft Research, that introduced a method called item to vec, but what it was, as you might have guessed, is they literally just got word to vec, pretty much, with some very minor modifications, and used it over collections of item IDs instead of words. So instead of a sentence, they have a user's session or shopping bag, and instead of words, they've got the IDs of the items that they viewed, or the IDs of the items that they bought. They used skipgram negative sampling version of word to vec, if you're into that kind of thing, and they got pretty decent results, right? Once you've got those individual item embeddings that are learned in an unsupervised manner, you can just literally take like the vector mean of each of the embeddings that appear together in a bag, and that gives you a usable representation of that bag or that set. So these things appear in search and text mining tasks quite often as kind of like lower bounds or baselines for more sophisticated measures, or more sophisticated algorithms. So for example, there's this paper about something called the word movers distance for calculating semantic distances between sentences, and they start off by calculating the word centroid distance, where they just get the embeddings for the words in the sentences, average them together, and calculate a rough distance between sentences based on the differences between the centroids of the words in each sentence. And then once they've done that, they use a more complicated method to actually rank or calculate an ordering score, distance score, based on the ones that are close from their centroids. Anyway, so it's kind of simple. Visually, you just get each individual item embedding, and you literally go through them and take the mean at every position in that embedding, and that gives you an embedding for the bag as a whole, or for the sentence as a whole if you're doing it in the text mining field. But there's a limit to how well these things do. They're not very task-oriented. The embeddings don't adapt to the problem domain because you've already trained them offline in an unsupervised, you've already trained them in an unsupervised manner, and now you're trying to use those embeddings to solve a different task other than the task they were trained on. So taking the mean of those embeddings may not always be the most useful strategy for the classification task at hand or the regression or whatever you're doing. So there's a slightly more sophisticated approach, which is pretty similar to that. In NLP tasks, people refer to it sometimes as like a neural bag of words, and you can extend that idea to be a bag of items if you kind of take the analogy of like a session is a sentence, or a shopping bag is a sentence, and the items in that session are words. So in this approach, you initialize the embeddings randomly, just like in word to vec, or you use pre-trained ones and then use this method to kind of fine-tune those embeddings. And then you take the mean, or occasionally the sum, but let's just stick with the mean as we were already talking about that before, across all of the items in a particular set or bag. And then you feed that mean into the network that you're training on your particular task that you're trying to solve, and then you update those embeddings via backpropagation. So it's basically the same as the previous approach, except you're learning the embeddings as you learn to solve the task of interest in your domain. So I've put output layer or rest of network up here. You know, it could be that you're trying to directly use the set embedding, the bag embedding here to solve some task, make some prediction, or it could be that you're concatenating that with an embedding for like the user or some session context, or you could be combining it in more sophisticated ways with user data or other metadata at the same time. It doesn't really matter. Basically, the idea is you've got these embeddings for the individual items, and you backpropagate the errors all the way through the network, so those embeddings adjust as you go along, rather than being something that you learn separately and then apply to a classifier. So then there's the extension of this, which I really want to get onto, is called deep averaging networks, which is from a paper from a couple of years ago that was really about doing things like sentiment classification and question answering tasks. And the authors were actually trying to find a cheaper alternative to recursive neural networks, the other kind of RNNs. If you're not familiar with those, they're used quite a lot in natural language processing, and they're basically kind of nested structures of neural networks that apply at the kind of constituent or phrase level going up the syntax tree for a sentence. And they're really good at certain NLP tasks, but they're very expensive to train. So what these guys wanted to do is they wanted to find a way of kind of composing the embeddings for the words in a sentence into a sentence embedding that was cheaper than recursive neural networks, which are doing state-of-the-art on this task, but got comparable results. So it's such a simple idea, it almost doesn't deserve a name of its own, but I mean, I'm sure people have done this in different tasks before and not called that something specific, but these folks, Iyyer and et al., came up with the name deep averaging networks, and there have been one or two papers since that have used that and used that name. So I guess maybe that name will stick, but like I say, there's probably prior art somewhere out there. Some of you have probably done something similar before anyway. And the idea is, basically, it's exactly the same as the previous approach, except instead of taking so you get the item embeddings here, these are initialized randomly, then you take their mean, so you get an embedding for the bag or set of the same size, same dimensionality as the item embeddings, and then you just feed that through a number of dense, fully connected layers, and then the output of that is what you then feed into your classifier, or what you combine with some other source of data in a more complex network. So then, as you're training it, you're updating not just the weights on the fully connected layers, but the embeddings themselves as well. And if you want to actually reuse these embeddings for a bag or set, separately from the context in which they're trained, it's the weights on the final fully connected layer there are what you then kind of would take off and export and load into another model or whatever. So how does this work? Why does this work? Well, the way the authors put it is the deep layers of the deep averaging network, that is the further on fully connected layers, amplify tiny differences in the vector average that are predictive of the output labels. So they kind of give this sentiment analysis example. So if you imagine the sentence, I really loved Rosamund Pike's performance in the movie Gone Girl. I think it was all right, personally. So yeah, maybe I might say liked instead of loved. But maybe someone else might say despised instead of liked. Now, if you take these three sentences, all of them are going to have pretty similar vector means, because all of the other words in the sentence, or items in the collection more generally, are the same, apart from the one that's actually, bearing the semantic information there. So what they did was they showed with some analyses of the weights on the different layers that as you feed this information through the deep averaging network, the DAN, it exaggerates the differences in the representations between sentences with, say, a positive and a negative sentiment in their case. They also contributed this idea of word dropout, which they found worked very well in this task, which is instead of performing like dropout after the fully connected layers, they actually dropped out whole words from the input data from individual sentences at random. So those things didn't contribute to the vector mean if they were dropped out. And I think that might be quite specific to sentiment and question answering tasks, where actually most of the words don't really contribute to the result you're after. I couldn't get it to work that well when I was experimenting with this on other data. So, moving on to that, I wanted to see if we could use this in something that resembled a recommendation task. So I did some really sort of short, sketchy experiments to see this. So there's a Kaggle contest going on at the moment about predicting reorders on Instacart data. Instacart are a bit like Ocado or something like that in the States. And so I boiled this down to a slightly simpler prediction task to the one in the contest. Just given a previous order of n out of about 50,000 products, can we predict what percentage of items in that order the same user will reorder next time? So I'm only using the item IDs in the order, not any metadata about the user or their previous history, just that single order to predict how many of them will reappear in the next one. So I tested head-to-head with a deep averaging network versus a gated recurrent unit, which a lot of people are starting to use for kind of sequence-based recommendations. They've got a similar number of trainable parameters in each. Actually, the GRU has got slightly more. I picked these numbers so they were similar between the two. So the GRU would expect to be able to learn better without saturating. Actually, after a single epoch, it does learn better. It gets to like a loss of 0.0614. That's just regressing on what size the next order, what proportion of items in this order will be reordered in the next one. But anyway, that's a bit of a toy example just to demonstrate that we can learn something useful here. The trouble is, one epoch of a GRU takes like 5 hours to train using Adam on a Google GPU instance with this amount of data, whereas one epoch of a DAN, which doesn't do as well, but is kind of comparable, takes like 4 minutes to train. And then if you keep on training the DAN, this is the training loss and validation loss over 5 epochs. By the third epoch, which is like 12 minutes, it's already doing as well on the held out data as the GRU did after like 5 hours of training. And the fact that the training loss is still going down suggests that with throwing some regularization in there, we might be able to get better performance out of that. I hadn't actually tried with any regularization yet, so this was just kind of a bit of a brief initial exploration. So I also tried it with a neural bag of items, so basically took out the hidden layers and just used the averages directly to predict the output. The training time was similar to the DAN, but it flattened out really quickly at a worse test loss than the DAN was doing at the end of its first epoch. As I say, this is not very scientific because there's no dropout, there's no weight decay or other regularization here, there's no normalization here. But I think it's kind of suggestive that if you've got data that has no order, or actually in this case does have order, but that order is of limited obvious value, then it might be worth trying something much simpler like this before going for a more expensive model like a GRU or an LSTM or whatever. Okay, that's kind of it. Thanks.